Isang magandang araw sa inyong lahat. In this video, magsasolve tayo ng isang problem patungkol sa first law of thermodynamics for control mass. So first, let me just read the problem for you. A piston-cylinder assembly contains 2 kilograms of saturated liquid water at 20 degrees Celsius. There is a linear spring mounted on the piston such that when the water is heated, the pressure reaches 3 megapascals with a volume of 0.1 cubic meters. Letter A, find the final temperature. Letter B, plot the process in a PV diagram. Letter C, find the work in the process. And letter D, find the total heat added in the system. So we are provided with a schematic diagram on the screen. Una sa lahat, isulat muna natin ang mga given, mga values na nalalaman natin according to the problem. The mass of the saturated liquid water inside your piston cylinder assembly is equal to 2 kilograms. So let me just write that down over here. Also, sinabi rin na ang initial temperature ng ating saturated liquid water ay 20 degrees Celsius. Since it is saturated liquid water, pwede nating sabihin ang quality at the initial point is equal to 0. So remember na kapag ang value ng ating quality ay 0, then we have a saturated liquid. If the value of the quality is 1, then we have saturated vapor. And if it's somewhere in between 0 and 1, then we have a saturated mixture. Okay? It is also mentioned na meron tayong linear spring na andito, no? So let's just take note of that right now, and makaka-apekto yan actually sa letter B ng ating problem. Not only in letter B, of course, in letter C, and magkakascade pa siya to letter D. Also, sinabi dito na after heating, the pressure of the water inside reaches 3 megapascals and the volume is 0.1 cubic meters. It means that P2, or the pressure at the final state, is 3 megapascals, or basically equal to 3,000 kilopascals. So I converted it right away because of the fact that our thermodynamic tables is in kilopascals. V2, which is the final volume, is equal to 0.1 cubic meters. So, yung mga bagay na pinapahanap sa atin, una sa lahat ay yung final temperature T2. Also, we are asked to draw the pressure versus volume diagram, or basically your PV diagram. And we are asked to solve for the work done in the process. So, tawagin natin W12, the work done from point 1 to point 2, or from state 1 to state 2. And finally, we are also asked to solve for the total heat added on the system, which we are going to call Q12. Alright, so here we have our energy equation. So ang una natin gagawin ay papasimplihin muna natin ang energy equation na to para maging mas maikli siya and mas friendly sa ating mga mata. So we can assume that your control mass is fixed in space. So anong ibig sabihin ng fixed in space? It means na hindi siya nagta-translate, hindi siya nag-rotate, or basically hindi siya nag-move from one point to another. So that means that the change in elevation is 0, which means that the potential energy component is just equal to 0. And also, since hindi siya nag-move in space, the velocities are 0, which means that the kinetic energy component is 0. It is mentioned in the problem that water is heated. Therefore, we would expect that Q is in our energy equation. So, hindi siya magka-cancel out. Whereas sa ating problem, makikita natin na itong piston na ito, this one over here, can move upward or downward, depende na lang sa pressure ng fluid na nasa loob, which means that there is expansion or compression, which means that work here is not equal to 0. So, we cannot drop it out. We also know that the internal energy is dependent on the temperatures of your fluid. And in this situation, since we are heating the fluid inside, we would expect changes in temperature and therefore changes in internal energy. Therefore, U2 and U1 will not vanish in the equation. Our final energy equation will then be Q minus W is equal to M multiplied by U2 minus U1. Whereas we already know M, that is just equal to 2 kilograms according to our problem, and we can solve for U2 and U1 using our thermodynamic tables. Now, let's define each state points using our thermodynamic tables. So, we have state 1. Alam natin at the initial state, the temperature is equal to 20 degrees Celsius. and the quality is equal to 0 because it is saturated liquid. Can we fully define the state already? Actually, the answer is yes because we already have the temperature at alam natin na ito ay saturated liquid. Alam natin yung quality. Therefore, we can say that the internal energy U1 is just equal to UF, or the saturated liquid internal energy at 20 degrees Celsius. Also, the specific volume at state 1 is just equal to the saturated liquid specific volume at 20 degrees Celsius. Also, alam natin na ang pressure at state 1, it's just equal to the saturation pressure at 20 degrees Celsius because of the same argument na ito ay saturated liquid. So again, if we have a saturated liquid, saturated vapor, or saturated mixture, then we can just use the saturation pressure as the actual pressure of your fluid. Now, let's inspect the thermodynamic tables to obtain these values. So we have temperature entry for saturated water. So let us just make sure that we are on the saturated water tables. Now, at 20 degrees Celsius, we know that VF, or basically the saturated liquid specific volume, is equal to 0.001002 cubic meters per kilogram. So let us just write that down. We have VF that is equal to 0.001002 cubic meters per kilogram. Okay? UF, on the other hand, it's somewhere here. We have 83.94 kilojoules per kilogram. And finally, we have the saturation pressure that is just equal to 2.339 kilopascals. Okay? So very easy for state 1. Now, why do we need to solve for the specific volume and also the pressure? It's because of the fact that they are required when we are going to draw the PV diagram. And speaking of the PV diagram, small letter v is just your specific volume, whereas we are looking for capital V, which is your actual volume. So we know the relationship between the actual volume, V1, with the specific volume. That's just equal to the mass multiplied by the specific volume at state 1. And we know that mass is just 2 kilograms, and the specific volume is just 0.001002 cubic meters per kilogram. We can now solve for V1. Let's just input that to our calculator. We have 2 times 0.001002. That is equal to 2.004 times 10 to the negative 3 cubic meters. So this is our initial volume. Therefore, our first point in our PV diagram is ang ating P1, V1, capital V, no? It's equal to 2.339 kPa, 2.004 times 10 to the negative 3 cubic meters. So now let's move forward to state 2. So we know that at state 2, the pressure is 3 megapascals. So let us just write that down. State 2. P2 is equal to 3,000 kilopascals. And unfortunately, that's just the only parameter that we know for state 2. However, we know the extrinsic property capital V2, which is your actual volume. And again, applying the relationship between the actual volume, this time for state 2, we have capital V2 is equal to M times small v2. We can actually solve for the specific volume for state 2. Capital V2 is just 0.1 cubic meters. It's going to be equal to 2 kilograms multiplied by specific volume V2. Finally, we can say that V2 is just 0.1 cubic meters over 2 kilograms, giving us an answer of, let's plug it into our calculator, 0.1 over 2. There we have it. We have 0.05 cubic meters per kilogram. This is the specific volume for state 2. Now, we have two independent parameters to fully define state 2. We can now consult our thermodynamic tables again. So let's just go there. This time, punta tayo sa saturated pressure entries, no? Para i-check kung saturated ba siya or superheated or compressed ba. Though it's unlikely that it's compressed or subcooled because we're adding heat to it. So let's go to the saturated pressure entries over here. We have 3,000 kilopascals. And as we can see over here, at 3,000 kilopascals, the saturated liquid volume is equal to 0.001216 cubic meters per kilogram. And the saturated vapor volume is 0.06668 cubic meters per kilogram. So makikita natin na yung actual specific volume ng ating system ay somewhere in between VF and VG, which means that it is saturated mixture. Take note, if the actual value of your specific volume is in between your lower boundary VF and your upper boundary VG, then it is saturated mixture. Same goes with your specific internal energies and specific enthalpies. Kung yung actual value ng U at state 2 is somewhere in between UF and UG, then you can conclude that it is saturated mixture. So now let's just put that on record that your actual specific volume, 0.05 cubic meters per kilogram, it is greater than VF, which is just, as we saw a while ago, it's 0.001216 cubic meters per kilogram, and this value, 0.05, is less than the value of Vg, which is just equal to 0.06668 cubic meters per kilogram. Lahat ng andito ay na cubic meters per kilogram. Okay? Therefore, we conclude that it's saturated mixture. There you go. That means that certain formulas apply. Certain formulas such as V2 is equal to VF at state 2 plus VFG at state 2 multiplied by the quality at state 2. Okay? So remember, this is one of the formulas that will apply if you have saturated mixture. Also, the other formulas that will apply if you have a saturated mixture are the formulas that I will flash on the screen. Now, we know VF at state 2, it is just equal to this one. And VFG, we can actually get the difference between VG and VF, okay? Or we can just consult our thermodynamic tables once again, giving us a value of VFG that is equal to 0.06546. So let me just fill in the known values. Finally, multiplied by the quality at state 2. Now, you can see this is a one equation, one unknown scenario, and we can just input it in our calculator and perform the shift solve technique. So if you don't know the shift solve technique yet, kindly watch out. So sulat lang natin literally yung equation sa ating calculator. We have 0.05 equals, so I pressed alpha and then this button, and then it's equal to 0.001216 plus 0.06546 multiplied by the quantity x. Okay? Press shift and then press solve over here, and then input a number that is between 0 and 1. So in this case, sabihin natin 0.5. So press equals, and then you have 0.745. So this is the value of our x2. Bakit natin sinolve ang quality at state 2? Because I just mentioned that the formulas that I'm gonna flash again on the screen are applicable and will help us find the value of the internal energy at state 2. That is U2 is equal to UF at 2 plus UFG at state 2 multiplied by the quality x2. And we know that UF2 and UFG at 2 are just values from your thermodynamic tables at 3 megapascals or at 3,000 kilopascals. Okay? Consulting our thermodynamic tables, we have UF that is equal to 1004.76 and UFG that is equal to 1599.34. Both of them are in kilojoules per kilogram. Let us just write them down. U2 is equal to 1004.76 plus 1599.34. All of them in kilojoules per kilogram multiplied by 0.7452, which is the quality that we just solved for a while ago, and again input in our calculator. So make sure that the inputted values are correct para siguradong tama yung ating sagot for internal energy at least. we have 2196.59. So let me just write that down again. So we now have our U2. What else do we need? According to our problem, we need actually to find the final temperature. And since we said that at state 2 we have a saturated mixture, it also follows that T2 is actually the saturation temperature at the particular pressure level that we are analyzing, which in this case is 3000 kilopascals. So inspecting our thermodynamic table very quickly, we have 233.9 degrees Celsius as the saturation temperature at 3000 kilopascals. So T final, or basically T2, is equal to 233.90 degrees Celsius. This is now our answer in letter A. Let's now plot the PV diagram. Plot the process in a PV diagram. We already know the first point, P1, V1. The second point, we're on the way there, P2, V2. We know that P2 is just 3000 kilopascals and V2 is 0.1 cubic meters according to our given. So P2, V2 therefore is equal to 3000 kilopascals, comma, 0.1 cubic meters. Okay? So this is now our second point in our PV diagram. Now let us draw the PV diagram of this process. We have pressure on the vertical axis and volume on the horizontal axis. Our pressure is in kilopascals and our volume is in cubic meters. Now, the saturation curve of our PV diagram looks something like this. Okay? So we know that our initial volume V1 is a really small number. So you have 2.004 times 10 raised to negative 3 cubic meters. And our pressure is also relatively small. We have 2.339 kilopascals. And we know that it is saturated liquid. So it means na yung ating point ay somewhere here on the left part of your saturated curve. So let's say that our volume V2 is somewhere here. It's equal to 0.1 cubic meters. And you know that it is located somewhere inside this saturated region because it has a quality that is between 0 and 1. Let's say our pressure is somewhere here, 3000 kilopascals. And our state point is located somewhere here. If this is 0.1, then we have 0.2 over here. So the thing here is that alam natin ang endpoints ng ating PV diagram. However, we don't know how these two are connected to each other. Is it connected by a straight line? Is it connected by a parabola? Is it connected by whatsoever curve? We don't know yet. Now, we are going to try to figure it out using the given that it has a linear spring. So take note that if we have a linear spring, we define this over here as the displacement x of our piston, then we can say that the spring force F is directly proportional with the displacement x. Also, let's say that the pressure inside your system is P. We know that the pressure P is just directly proportional to the force F. Why is that so? Dahil alam natin na F is equal to P times A, right? And the cross-sectional area here is the cross-sectional area of your piston, which is just constant. So therefore, we can say that the pressure is just linear with your spring force. From here, we can deduce that pressure is actually directly proportional, or at the very least linear, with the displacement x. Now, how is it related to the volume? Recall that volume is basically the cross-sectional area multiplied by the displacement x, right? Whereas A is a constant, so we can say that the volume is directly proportional with x, or rather, volume is linear with x. Now, this statement and this statement over here can be joined together, and we can say that from here, pressure is actually linear with volume. This can actually be shown using a more complicated mathematical derivation using the first law of motion. But for now, we can conclude using this logic that pressure is linear with the volume, which means that our points 1 and 2 are connected with a straight line. Therefore, our PV diagram looks something like this. There you go. This is our answer to letter B. Now for letter C, we are asked to solve for the work in the process. So we know that mathematically speaking, work is just the integral of P dV. So we have W is equal to the integral of P dV, which means that work is just the area under the PV diagram. And if we are going to utilize the PV diagram that we just drew, work is basically the area under this curve. And if we apply the fundamentals of geometry, we are essentially looking for the area of a trapezoid, whereas this one over here is your B1, right? Plus B2, which is your second base, divided by 2, multiplied by the height h, which is, in this case, this height over here, the distance between the two bases. And if we inspect further the PV diagram, B1 is just the initial pressure P1, B2 is just the final pressure P2, and H is just the change in volume V2 minus V1. So now, modifying this formula, we can now get the area under the PV diagram. So let me just zoom that out para mas makita natin. So basically, we have P1 plus P2 all over 2 multiplied by V2 minus V1. Filling in these values, we know that the initial pressure P1 is just equal to 2.339 kilopascals plus 3,000 kilopascals all over 2 multiplied by 0.1 minus 2.004 times 10 to the negative 3. Now, what is the unit of work in this situation? Remember that your pressure is in kilopascals and your change in volume is in cubic meters. We also know that kilopascals is just kilonewton per square meter. We have cubic meters over here, which will just be equal to kilonewton meter or kilojoules. Okay, so our work is in kilojoules. Now, substituting all this in our calculator, we have the following as the work done by the system. W is equal to 147.1086 kilojoules. This is our final answer for letter C. Alright, moving forward to the last unknown of this problem, we solve Q for process 1 to 2. And we actually derived our equation a while ago, our energy equation for this scenario. We have Q minus W is equal to M times the quantity of U2 minus U1. So let us just write that down over here. We have Q12 minus W from 1 to 2 is equal to M multiplied by U2 minus U1. Transposing W to the other side of the equation, we have Q from 1 to 2 is equal to M multiplied by U2 minus U1 plus W from 1 to 2. And since we know all these values, let us just substitute them in our governing equation. We have 2 multiplied by 2,196.5882 minus 83.94 kilojoules per kilogram plus 147.1086 kilojoules. Entering these values in our calculator, we have the following. Our final answer is 4,372.405 kilojoules. Q12 is equal to 4,372.405 kilojoules. This is now our final answer for letter D. Alright, ito ang kabuuan ng ating solution for this particular problem. If you have questions, just comment down below. I hope you learned something and see you in the next videos.